Hi everyone, welcome to my workshop. With this welding mask, I want to symbolize that today we're going to do an experiment involving a lot of bright light. I'm going to make an Edison bulb and I'll show you how it's done. You on the other side of the screen are completely safe. At most, you'll just see a very bright light on your screen. It'll turn white, but there's no danger to you. What should you know about the Edison bulb? Well, one thing for sure is that when you go into a store and buy a bulb, like this one here in my hand, and you see here on it that it says E27. The E stands for Edison. Edison patented this socket at the end of the 1800s, and we've been using it in many places ever since. Of course, there aren't just traditional bulbs. There are also compact fluorescent lamps, LED sources, and so on. All in all, this traditional filament, which you find in the Edison bulb, was pretty much dominant until 1970. Then came the compact fluorescent lamps, neon tubes, and then the LED sources. So, for energy efficiency reasons, people started switching over to compact fluorescent lamps and LED sources, since a traditional bulb has extremely low efficiency. Only a few percent of the invested energy is converted into light. Compact fluorescent lamps are somewhat more efficient, and LED light sources are also somewhat better. But of course, everything has its good and bad sides. For example, when we turn on compact fluorescent lamps, for quite a while we basically don't get the brightness we want. LED light sources provide this instantly, and traditional incandescent bulbs also practically deliver that brightness right away. I have good news for those who aren't big fans of compact fluorescent lamps or LED light sources. The traditional filament bulb might actually make a comeback, so to speak, because with nanotechnology, these bulbs can be, let's say, turbocharged. With nanotechnology, they surround the tungsten filament with a nanotech layer, which act like a shield. It lets the light through, but the heat, it reflects back. And this way, the efficiency of the bulb will be about 40%, which is very good, better than that of an LED light source. Personally, I hope that sooner or later traditional light bulbs will make a comeback. Traditional in the sense that nanotechnology will be used, and we'll get a very efficient traditional bulb. At the end of the 1800s, a lot of interesting things happened. One of the things, as I mentioned, is, for example, Edison's patent and the socket, but among other things, it was also decided at that time whether there would be alternating current in the outlets or direct current. There were two rivals, one was Edison and the other was Tesla. Tesla said that alternating current was needed, while Edison said that direct current was needed. One advantage of direct current, for example, is that where it is generated, it is extremely simple to connect the units, the power generating units, in parallel. The advantage of alternating current, on the other hand, is that it can reach long distances. It probably wasn't easy to make a light bulb at the end of the 1800s either. It's not some kind of puzzle box or a space comb, it's just a light bulb where basically a tungsten filament glows under a glass bulb. Still, a lot of things were needed just to get even a little bit of it to work at all. To create a working light bulb, I've placed various items here on the table, and I'll show you how it's going to work. First, this is a graphite pencil, a 2B, and I've extracted the inner graphite rod from it, so you can see what the pencil looks like. Why did I take out this graphite rod? Well, because Edison also first tried to make a light bulb from this. He made graphite filaments from bamboo fibers in some automatic way, and he heated up these graphite filaments until they glowed. Graphite is a really interesting material. It has a similar melting point to tungsten, which is used in traditional light bulb filaments. At the beginning of my video, I mentioned a few things about how when we buy a light bulb at the store, for example, we can see that it's an E27. We can also see how many watts it is, and we can also see on it, for example, that this particular Edison bulb, it says on it that it's 3000 Kelvin. 3000 Kelvin means that if a tungsten filament glows at 3000 Kelvin, that's what it looks like a tungsten filament glowing at 3000 Kelvin. This is the warm white light, a bit yellowish. The first bulbs usually used 2200 to 2400 Kelvin, so a lower temperature, which is why their color was more yellowish. However, this had a very good effect on their lifespan. One of the first Edison bulbs was at a fire station and has been operating for more than 100 years to this day. But don't imagine that bulb is something that gives off a huge amount of light. It was really more like a glowing ember. Another interesting thing, if we're talking about so-called traditional bulbs, is halogen bulbs. So the thing about halogen bulbs is that inside the bulb there's a special gas, for example with good content, and there's a process called the halogen cycle. If you have a filament that's glowing, it evaporates. As a result, it gets thinner and thinner, and eventually it just burns out. However, in a halogen bulb, the halogen cycle starts at a certain temperature, and the evaporated material gets redeposited onto the tungsten. In fact, it gets redeposited exactly where the material is thinnest because that's where it's hottest. So, halogen bulbs are also very good. That's why they were able to increase their brightness, so to speak, because the halogen cycle helps. The filament doesn't burn out very quickly, it's relatively durable too, but its efficiency isn't that great either. It's not even close to the current LED light sources. Have you ever stopped to consider these compact light sources? Let's take a closer look to see exactly what the classic vintage Edison bulb is actually made of. Maybe you are now wondering how you can carefully extract the thin graphite rod from a standard wooden pencil. I'll let you in on a little secret. One effective trick is that you simply have to set it on fire. Basically, what happens during this process is that the surrounding wood burns off the graphite rod. That is one straightforward and relatively easy method to consider. Interestingly enough, the other possible solution is to sharpen both ends of the pencil, as you can see here, and then apply voltage to it. Current will flow through, the graphite filament will heat up, and basically the graphite rod will fall out. So that's how you can extract the graphite from a pencil, though there are other methods too, but I won't go into those now. You can also see other things on the table here. This is a power supply. You can adjust the voltage and current of the power supply. It can output up to 28 volts, and roughly it can handle up to 16 amps at most, which you can control with these potentiometers. I see a black tube here. The other end of this black tube is connected to a vacuum pump, and with this, I'll be able to suck the air out of the jars. I made a stand like this, as you can see here, and we can set up the units on this stand. Let's start with the candle experiment, so we'll need the other one for that. The candle experiment goes like this. First, you need this stand. This is the candle, and it will keep burning right here until all of the oxygen finally runs out. Here is the copper filament, which I will carefully secure. Here is the glass jar that will go directly on top. Alright, now I will turn on the power supply unit. You can see the display screen here. The top row shows exactly how many volts it is outputting, and the second row shows how many amps are flowing through. I will slowly lower the voltage. Now I will light the candle. Alright, the candle is burning nicely. The candle is burning, burning. Don't let it go out. Let's see. It will soon use up the air inside. By now, there is definitely very little oxygen left in there. It's important to remove the oxygen. You saw the experiment. The filament burned up very quickly. So this was a very short experiment. And this is the result that formed, which the copper wire couldn't handle, and it melted. So it's not worth making a filament out of copper, because, as they say, it will have the lifespan of a mayfly. It melts very quickly. No problem. We have another filament material, graphite. In this packet, there are HB half millimeter diameter leads, pencil leads. I think the graphite filament will last longer here. Let's see. We have to wait patiently until the candle flame completely goes out, because that is the exact moment when it consumes the remaining oxygen, and by then there will definitely be very little oxygen left inside the glass jar. Now, let us see what will happen next. I will start gradually increasing the voltage. I will wait a little bit. As you can clearly see, here too, the glowing stopped pretty quickly. And this truly shows what a remarkable genius Thomas Edison was. He was able, back then, over 120 years ago, to successfully create. Take a look at this lamp. Even here, with our so-called modern technology, it's still quite a struggle. And what exactly happens if the graphite filament is exposed to the open air? Well, that was also a very short experiment. After a bright flash and a bit of welding, the graphite filament simply ceased to exist. It just burned through in several different places. Now, let's bring out the big gun. I'm going to break off a small piece from this. This is a nice, incredibly thick graphite rod. I successfully managed to install the thick graphite rod taken from the pencil. Now we must prepare for the bulb. We have to wait patiently for the candle flame to completely go out. The thick graphite rod basically exploded during the process. I will try the procedure again, and maybe we will get a much more spectacular experiment this time. Now you can clearly see that 4 volts are going out and 3 amps are flowing, which means that is about 12 watts of power. At 12 watts of power, there's still absolutely no light visible. At 2 volts and 8 amps, the graphite filament exploded just like it did before, releasing a lot of thick smoke. So, overall, it seems you still can't make a truly good incandescent filament out of this material. Let's see if the upcoming vacuum experiments yield any different results. I've already installed the vacuum electrode holder. It's specifically called vacuum because you can suck all the air out of the glass jars through this long black tube. There is a manual valve right here that I can easily close, and there is a precise instrument that clearly shows the level of vacuum inside. As I mentioned before, the melting point of nickel chrome is significantly lower than that of graphite, so when it glows brightly, you can expect a more yellowish light, but it is a very resistant and very sturdy material. I have now closed this valve here, so no air can get under the glass jar, and the lid of the jar even dents in a little bit. The electrical wires are properly connected. The electrode is positioned inside, 4 volts, 15 amps, and at this point nothing happens yet, but that's already a significant current. 7 volts, 15 amps. There's just a tiny bit of light, and now the light is coming in properly. I'll lower the power a bit and show you up close. Here you can see that the nickel chrome wire holds up really well. The jar is under vacuum, and it's glowing nicely, so to speak. If you look closely at the filament, you can see it is starting to radiate quite intensely now. If I increase the electrical current flow much higher, or more precisely the power, then this wire will probably completely burn out and fail. As you know, the product of the two is the power, meaning 6.5 and 15.8. So this lamp consumes a significant amount of energy, but it doesn't give off much light. It's definitely worth increasing the power even more, so let's see exactly what happens next. So what we have here is 10 volts, 16 amps, and 160 watts. An enormous amount of power is going in, and there's barely any brightness. And actually, I can feel with my hand that a tremendous amount of heat is being generated. It's literally hot here. And now that I've turned the power down, the wire is starting to cool off nicely. So you could actually make a lamp with this. The efficiency isn't very good. I just put in 160 watts, and if I got the equivalent of 20 watts of light out of it, that's already something. My tungsten now, unfortunately, I don't have any. I went into a few stores and tried to buy a traditional bulb, thinking I could break open the glass, but these bulbs have been phased out so much that I couldn't get my hands on one, so I managed to get some nickel chrome instead. Let's see how copper and the two types of graphite perform. I put in the thin little copper wire, pumped out the air, so now there's almost a vacuum under the glass, or at least the pressure is very low. And let's see. Remember earlier? It burned up very quickly. The same thing happened this time as well. The main issue here is that copper's melting point is much lower than that of the other two materials, nickel chrome and graphite, so you can't really count on it. So you can note that it's pretty hard to make a bulb out of copper. I installed the half-millimeter diameter graphite rod, like this. If you remember, in the previous experiment, this one didn't last very long either, so let's see what happens now. So what we have here is exactly 40 watts of power. With 40 watts, there is just a little bit of glowing visible, so let me show you that up close. At least I managed to make sure the filament didn't burn out quite so quickly this time, and you can see the graphite rod is glowing. Still, there is really not much brightness to speak of yet. The current has already started to drop down. I will give it a little more power now. Speaking of power, let's see what it can actually do. Even at a much higher brightness level, it lights up quite nicely, so it holds up pretty well overall. The vacuum really did its job effectively, even though the candle was just a simple DIY thing. Here too, the power consumption is extremely high. At 6 volts, it draws 8 amps, which equals 48 watts, but at least there's some light. The current is dropping now, which indicates that something inside is starting to fail, probably. So even if you are being extremely careful with your setup, you could actually make some pretty good and impressive lighting just by using a simple graphite rod. I have a brand new idea for this experiment. I am going to put every single one of them in there right now, and let's see exactly what happens right away. To be honest, I am really quite curious to see the results myself. I have carefully removed all of the remaining air from the chamber using the vacuum pump to create a perfect environment, just like this. And now that everything is finally ready, let's go for it and see the power. At this very moment, all 8 of the graphite rods are glowing with an intense light, and it is clear that the power supply unit simply cannot deliver any more electricity than this current level. Heating up such a large number of individual graphite rods requires such a massive amount of energy that the total current draw has basically maxed out the system's capacity. It is currently pulling 17 amps at a steady 4.5 volts, and even reaching 18 amps. Something else quite significant happened during this process too. I definitely did not design this specific electrical circuit to handle a sustained load of 18 amps. The protective insulation has completely burned off one of the main cables, so I am going to turn this unit off right now and carefully fix the damaged cable. I have decided to set aside this little DIY power supply for a moment and use the much larger inverter welding transformer instead. It can be easily adjusted all the way from 20 amps up to 240 amps. That should definitely be more than enough power for this task. I also swapped out the original wire for a significantly thicker one. I think these specific wires can handle up to 30 amps for a short time. I have manually set it to exactly 66 amps. There is definitely some visible light coming from it now. The thin graphite filaments are glowing quite nicely. I am pumping a truly crazy amount of electrical energy into this setup. The surrounding air is practically heating up from the intense heat. It consumes a massive amount of power, and while there is some light, it is honestly not that much. I am very curious to see what the absolute maximum is. Let's take a closer look at this. Well, this is certainly something quite interesting already. I didn't quite reach the level of 240 amps yet, but let's see exactly what happens when we push it to 240 amps. The entire inside of the glass jar has now turned a dark shade of gray. I'll show you the final result of this experiment. Everything inside is completely burned up and destroyed, or at least the delicate filaments are. So let's examine the damage more closely and see what we can learn from this. There's still one more experiment to do, the thick graphite rod. This one here. The lid of this jar, well, it's not heat resistant at all, so I have to be very careful to cover it. Vacuum for sure. Take it apart into pieces. I've placed the graphite rod inside now. You can see here that the previous experiment really took a heavy toll on it, here on the electrode holder. Everything is ready. The vacuum is set. The transformer is ready. I'm turning it on now. It starts at exactly 20 amps. That's 20A, and with a bit of smoke, the graphite filament basically snaps right away. To sum up the result of the experiment, I'd say you can do it the way Edison did, but its lifespan will be extremely short. Edison was a real genius back in the day, when he created all this at the end of the 1800s, and he didn't make a bulb that only worked for 5 to 10 seconds. As you saw, you couldn't make a filament out of copper because copper has a low melting point, so when it heated up, it burned out very quickly. Graphite is very good. It has a melting point of 3,500 degrees. It takes quite a lot of power to practically produce light. That's why they didn't use it, and actually, such a filament is very fragile. That's why wolfram spread. Do wolfram? It has exceptionally beneficial and versatile properties. And with that, this is the final concluding statement for today. Thank you so much for watching my video, and if you liked it, please make sure to give it a big thumbs up and subscribe to my channel. Bye!